So, hi everyone and welcome back to the channel. Now in today's video we're going to do a very deep dive nerdy analysis of how the classified hub system actually works, because it's not witchcraft, it's just a single stage planetary. And we're going to look at the efficiency claims that Classified put out in their own white paper. It's not peer reviewed, but I'm going to try and peer review it in this very video, their own white paper, in which they went into the efficiency results of their numerical evaluation method, so using maths, and also on a bench test. I am using my little crib sheet here because there's quite a lot to get through. I've been working on this series of videos for about 4 weeks now because I want to put a few kind of myths and theories to bed. I mean, I've got absolutely no bias on the outcome of this efficiency test, on the outcome of their internal testing or my testing, which I have done, and you'll see the results of my efficiency testing in the next video, and it's super, super interesting. Like I said, I've got no bias on this hub system. I do really, really like it for its mechanical engineering. It's kind of a masterpiece of packaging. Now, when I mean packaging, I don't mean cardboard and the plastic that is posted to you in. I mean the kind of engineering interface and fitting it all in such a small space to a weight spec. That's quite impressive. But I've got no bias. I'm not being paid to make these videos by Classified. Obviously, they've sent me a wheel set to evaluate, and they must be pretty confident because they know I'm going to do this kind of deep dive, and I'm just genuinely interested in this product because I think A, it could spell the end of the front mech, and B, it unlocks all the limitations of one by. So it's kind of two birds with one stone. Now you'll see my physical testing in the next video because there's just too much to put into one video. This is going to be a bit more theoretical, and I'm going to go through some of the drawings. I'm going to describe how the planetary system works. I'm going to describe the Classified section view, which is not classified because I've got it, it's in public domain. I'm going to describe the gear ratios and how they work and the packaging. I've read a lot of that online in YouTube videos and forums and said, well, we've had Sturmey Archers for years. Well, yes, we have, but there's one key component in here that makes the packaging really, really clever and keeps it so small. First of all then, let's see how it works. So I'm going to record the screen. This is going to be a bit geeky, but the next video will be the fun outdoor one and all the riding and mechanical kind of evaluation of the system. But let's just take a really quick recap of how it works, just in case you don't know. This is a very simple schematic of a single stage planetary gearbox. We've got a ring gear here in green. These purple ones are called the planets. The magenta ones are called the planets. We've got a sun gear in blue. And this kind of salmon coloured piece is what's called the carrier, the planet gear carrier, and that holds the planets in space and actually rotates with the planets. Now the bit that goes on the wheel is it's a dead part. There's no moving systems in the wheel. It's all the tricks are in this part. In this part, the carrier, so the salmon part, which is connected to the planets, are connected to this central silver anodized drive shaft. The ring gear is essentially where the cassette mounts on, and you can see on this one the cassette actually mounts around these lugs right on the outer periphery. You can also almost see some fretting already on those. I've got the same little picture up there on the top right. Now, in the Classified one, it's worth noting there are actually 6 planet gears, and in my little schematic I've only got 4, but it doesn't matter. The number of planets is analogous. It doesn't change the gear ratio or anything like that. It changed the kind of load on each teeth and stuff and how the torque is distributed around the circle, but number of planets doesn't matter. And this is about the same ratio as what's going on here. I'm not sure if the mod number, which is basically the tooth size, is exactly correct in my little schematic, but we've got a 1 to 0.686, which is basically means 1 turn of the cassette will give you 0.7 turns of the wheel. So that's your reduction gear. So it's a 0.7 ratio. Let's go through, before I get too dry mouth, let's go through the Classified hub labeling all these parts. And it's taken me quite a while to make sure I've got this right, and I have cross-checked it with Classified, so I do have a good understanding of the hub. So the ring gear, which is the outer part, is the piece labelled in green. Now actually the ring gear extends down here as well. So this is the ring gear, it's where the cassette bolts on, and the cassette is fixedly attached to the ring gear, it doesn't move. The next part is the magenta parts, the pink parts. These are the planet gears which orbit the sun gear. The next part I've drawn here is the planet gear carrier, which is actually fixedly connected to this central drive shaft which connects to the wheel. So the carrier for the planet gears is what's driving the wheel at all times. The load always goes through these teeth into the wheel. And then the sun gear is the blue bit in the middle. Now you can actually see a void under this blue bit, and you're like, oh, that's not actually, how's that actually touching the central hub axle? So this center part through here is what I call the hub axle, not the through axle. Through axle doesn't do any kind of load bearing. This is the hub axle, and you think, well, the sun gear looks like it's floating on the central shaft, but it's not. And through looking at some other drawings through the patent, I've kind of figured out what's going on here. This is actually a Sprag clutch, or a one-way bearing, and it's basically a needle roller bearing. So although this looks like a void here and here underneath the sun gear, which is attached to the hub axle, it's actually on a one-way clutch. Now, you can see these aren't voids, these are actually needle rollers. So that sun gear can spin on the hub axle one way, but it can't spin the other way. And that is when I come back down to how this works, is the super clever bit about for me, it's one of the most clever parts of this hub, unlike a Sturmey Archer or something like that, which uses a very complicated kind of clutch and fork mechanism with pulls to change gear. This changes gear passively by using a one-way clutch. And we'll come to how it works in a minute. But anyway, if we quickly look at an animation of the two systems, so let's say we're in the 1-to-1 ratio. So you're basically using it like a normal hub. You put your torque and your speed into the cassette with the chain, and the wheel speed's the same. The wheel spins at the same rate. That's the 1-to-1 ratio. There's no gear reduction, it's normal. Now in that case, what happens is the electronic actuator, which the inducting coil is inside the through axle, mechatronically switches a series of pulls in this part here, which is kind of what you'd call the clutch, and basically locks the carrier, which is the magenta part, to the ring gear. So the ring gear and the carrier are then spinning at the same rate. And what that does will just pull the sun gear around with it. And because the sun gear is attached on a one-way bearing, the sun gear will just spin as well. And the whole three components of the planetary spin together. This bearing, which actually is a 6707, it's actually quite a large bearing, a thin section bearing. I'm not sure if you can see it, but it's just in there. That actually is completely static in the 1-to-1 ratio, so that's bypassed. So there's no bearing loss from that, and we'll come to that when we talk about the losses document. There's no loss from that. So essentially you're just spinning like a normal hub. You're spinning on this bearing, which I'm pretty sure has been up-revved. So this bearing here is a back-to-back angular contact setup, matched pair angular contact setup to take out any axial displacement and to give it a very stiff axial kind of location. I believe they've gone away from that, and now they're using a single row deep groove ball bearing with a tolerant spacer, just like any other hub. And that's for a couple of reasons: for cost saving, simplicity, and slightly lower drag as well, because these back-to-back angular contact bearings are very good for axial rigidity, but the free spinning drag is quite high. So I'm pretty sure they've gone away with that. But anyway, I digress, that's besides the point. In the 1-to-1, let's start again. In the 1-to-1 ratio, it's spinning like a normal hub on the axle bearings. This one, which is now one bearing, and this one here. This one here is bypassed because the green and the red part are moving together at the same speed. So although it's rotating, there's no relative motion between the outer and inner race, so there's no drag coming from that. But it is still spinning on this one-way needle roller bearing here. And you have to remember that. So that's when you're in the 1-to-1 ratio. There's no gear reduction, everything spins together. When you press the button, what you're doing is you're obviously shifting down into the virtual small chainring. But what you're actually doing is unlocking the coupling between the Planet Gear carrier and the ring. So now this part and this part can spin at different speeds. And what that does, naturally, that'll have a natural torque reaction which will kick the sun wheel back the other way. Now, if you didn't hold that sun wheel back the other way, all that would happen was the sun wheel would spin inside here. However, this is where the really clever bit comes in. This one-way bearing in here doesn't allow that sun wheel to kick back the other way. So then the torque is reacted, and the torque then goes to the wheel through the carrier, and that's how it all works. So it's very clever, because this locking of the sun wheel is basically a byproduct of unlocking the carrier to the ring gear, and the sun wheel tries to rotate the other way, but it can't, because this one-way clutch, it has a number of needle rollers, and those needle rollers rise up on a ramp, and it jams the sun wheel to the shaft, and it can't move. Therefore the output goes through the carrier. Now we have relative motion between the carrier, which is this drive shaft, and the cassette, which is where you get your reduction ratio from. Now there is a relative motion in this large bearing, and the relative motion is 70% of the cassette speed. So if this green part is spinning at 1, this inner race and the salmon coloured part, which is the carrier, which drives the wheel, is spinning at 0.7, and that's your reduction ratio. So that is essentially how it works. The clutch mechanism of pulls and springs and detents and everything that lock and unlock the coupling of the carrier to the ring is very, very complex. And that is another barrel of drawings that I'm not going to go into in this video, because that's not really so important about how the gearing works. The most important thing that I nearly missed, and it took me so long to look at this and figure out what was going on, is that this one-way bearing, because before I was thinking, well, that's just in space, there must be something supporting it there, and it looks just like a needle roller bearing, but it's actually a ramped one-way bearing, and that's essential for when that sun wheel tries to kick back, it locks itself to the shaft. Now, what stops the shaft spinning? If the sun gear is locked to the shaft, and the central hub or the shaft is not fixed, what stops that just spinning inside the bike? Well, the clamping of the dropouts provides some torque reaction on the end caps, but that is exactly where that weird torque arm thing at the end comes into play. That has to brace the torque, the reaction torque. If that torque isn't reacted, what will happen is the sun gear and the shaft will just spin. The hub axle will spin inside the wheel, and you'll go nowhere. So without that torque arm, and without doing the through axle up nice and tight, you'll go nowhere, and the sun gear and the shaft assembly will just spin backwards. So it's essential that torque arm is there. It's a bit messy, as I'll describe in the next video. That torque arm is a bit messy because it doesn't fit all bikes. You have to kind of shim it a little bit with spacers, and there's a number of different torque arms depending on the size of your brake mount. And it's putting all that pedaling torque, it's reacting it through the brake mount, which is a little bit of a, it's not a bodge, but it's not what the brake mount was designed to do. So that's how it works. Now, I hope that is somewhat clear, but if you just want to pause and go over this a number of times, you'll get it, and otherwise you just can't really see what's going on. The switching mechanism part is all on this area here, and you can see a number of the pulls and springs. It's very, very clever how that works, which I could go into another video. But in terms of the packaging, it is a bit of a masterpiece, and it's all so small because they use this one-way bearing. If you didn't have that one-way bearing, you'd almost need another mechanism to be switched to lock the sun wheel. So that, I think, is pretty clever to use that. Now, I'm pretty sure that's an off-the-shelf part, judging by the size of it. If this does look like a scale drawing, I could probably find that one-way bearing. They may have modified it a bit, maybe on the outer race or something. And there's certainly what looks like a press-fit collar that's on the central hub axle, because the central hub axle will be aluminium for light weighting, but you wouldn't want that one-way bearing ramping into that. So there's probably a steel collar press-fit onto the hub axle to protect it, to take that compression load from the one-way bearing. Anyway, boom. Next, I'm going to talk about the efficiency claim. So about 3 weeks ago, I think Classified released on their website a white paper, not peer-reviewed, of 2 methods to analyze the efficiency of the reduction gear of the hub: a numerical method using maths, and a bench test, which is like a torque test rig. There are a few holes in it, which spurred me on to do my own testing. And I just couldn't wait to do my own testing, repeated testing, to sort of kind of compare. But on the whole, I think it's very, very good. Now, the document, first of all, I'm not going to go through it all because it's absolutely massive, but it gives you a brief description similar to what I've given you, but it doesn't show you that very in-depth kind of cross-section, and I hope I've explained a bit further how it works. But basically, they talk about load-dependent losses and load-independent losses, and the different parts of the hub which are responsible for both. So load-dependent losses basically are the gears and the bearings. This is anything related to torque and power. And the load-independent losses are basically seals, viscous drags, and kind of grease squeezing between gear meshing and stuff like that. Now, load-independent losses generally go up with speed and aren't affected by torque. So it doesn't matter how much torque you put on the hub. The load-independent losses, like bearing seal drag, will just go up with speed pretty well linearly. Now, load-independent losses go up with load. So gear meshing losses, gear sliding, gear rolling, and bearing sliding, that goes up with torque and load. So the more load you put on it, the more those losses go up. But in general, I mean, I can summarize a few parts of the document for you, but at 300 watts at 30 kilometers an hour, in the reduction ratio, the load dependent losses are about 70 parts to 30 parts load independent losses. So the kind of torque and power dependent losses of the actual gear meshing is the predominant loss. However, the load independent losses go up very quickly with speed. So bearing seal drag and things like that, the viscous losses, the faster you go, the worse they get. And actually, in total, the hub it works best at low wheel speed and high power, which is exactly what you'd use the reduction ratio for. So if you're talking about using it as a bailout gear for climbing, or basically the virtual small chainring, it's most efficient in exactly that operating window, exactly when you want it. It's not so efficient if you're using the reduction ratio at 40 kilometers an hour in a paceline, but you would never use it in that scenario because you wouldn't have the gearing to do so, and you wouldn't be in the reduction ratio, you'd be in the 1-to-1 ratio. So there are limitations of it in terms of the losses, but it is actually kind of, by virtue of the planetary gear system, it is most efficient at high powers, high torques, and low wheel RPM, which is exactly when you'd use it on steep climbs in gravel and mountain biking and road riding as well. So those are a bit about the load dependent losses. Now, that goes in the document to numerically calculate the load dependent losses. As you can see here, there's a gear friction, there's a gear face, like a mesh. They call this thin slice meshing calculation, where they take many kind of discrete points along the width of one gear tooth. And that can all be summed to calculate or predict the gear losses. They go on to predict the oil or grease squeezing losses. Now, there's a lot of literature out there for oil lubricated gears, not so much for grease, so take that with a pinch of salt. But that all comes out in the wash in their bench testing further on down in the document. And then there's a bar chart here, which is quite helpful to get your head around this load dependent versus independent thing. This summarizes the whole loss system of the numerical method. So we've got the total power loss here as 2.49 watts at 300 watts and 30 kilometers an hour kind of wheel speed. And this is an efficiency of 99.2% in the reduction ratio. We can see the biggest one is main bearing seal friction. So that is nothing to do with the classified hub system. That is present in every single hub. So you'll get this main bearing seal friction in a DT240. So the overriding friction is present in other hubs as well. The actual gear sliding friction and the load dependent losses are actually quite low, so 0.37 and 0.2 watts. Now you may think, oh, hang on a minute, the one-way bearing drag is not mentioned in this chart. They haven't analysed the friction of the one-way bearing. Well, don't forget, in the reduction ratio, the one-way bearing doesn't move because it's locked, it's jammed, because it's that one-way clutch, it's on the ramps, it's jammed. The one-way bearing is only in use in the locked ratio. Did I say that right? In the reduction ratio, the one-way bearing doesn't move. In the locked ratio, it's spinning. That needle roller bearing is spinning, which is why on the next graph for the 1-to-1 evaluation, they have included the one-way bearing friction, which is actually very, very low, because I've clarified this with classified. The one-way bearing friction doesn't have a seal because it's buried deep inside. It doesn't really need a seal, and it would be impossible to seal anyway because it's a big needle roller which moves up and down ramps. So scrolling on further through the document, this video is going on way too long and you're probably switching off, but I could make this video into an hour before even the next ones come out. These maps basically show you that the efficiency of the hub, well, that's the bench test. These maps show you basically the efficiency of the hub decreases with wheel speed. This is the main takeaway from this, is that if you're going to be bombing along the flats and in the reduction ratio, the efficiency goes down, or the losses go up. If you're talking about what's worst, high torque or increasing, or doubling the torque or doubling the speed will be worse in terms of the efficiency. And then they go on to talk about the actual bench test. I've actually worked and designed systems like this for robotic actuators to look at efficiencies of harmonic and cycloidal drives. So I'm very familiar with this kind of back-to-back torque rig setup. There's an input, there's an output, there's two load cells. You measure the power in and the power out, and that gives you your efficiency. But there are a few omissions from this system, which is practical. You can't test everything. Now, going back to the bearings quickly on the bearing losses, it's actually all pretty simple, hub stuff. So I'm pretty sure we've got 6 6803, there are two kind of DT Swiss sized bearings, what I would call non-standard, like SKF or NTN bearings. They are a 17287 and an 1837. They are kind of non-standard bearings, but they are standard because they're so widely made now by Enduro and DT Swiss. And that is replacing this double row angular contact back-to-back setup. And then we've got this big 6707. Now, like I said a minute ago, this 6707, this big one between the carrier and the ring gear, that most of the time, if you're in one-to-one, is completely stationary. Yes, the whole thing spins, but there's no relative motion there. So there's no ball drag, no seal drag in that, nothing. And in the reduction ratio, it's spinning, but only 70% of the cassette speed. So there's only a very small relative speed difference there. Now, when we go to look at the actual bench testing results, even though it does test, it tests everything. It tests all the gear meshing, the load dependent and the load independent losses, the speed related losses, tests all of that. We can see that actually the lowest efficiency that they get is at quite a low power and a high wheel speed, like I said, so 200 watts and 30 kilometers an hour, which is probably, you're never going to use the reduction ratio in that range, because you're 30 kilometers an hour, you wouldn't be in the reduction ratio, you'd be in the one-to-one in the sort of bigger chainring mode. So it's not really that helpful, but it's actually the lowest efficiency. So it's 98.98 efficient in that scenario, which is still pretty damn good. It's still pretty close to 99%. So I would say throughout their whole testing, 99% is their lowest efficiency testing. Now, what will my outdoor testing achieve? Now, my outdoor testing will be at a higher power and a lower wheel speed, so it should be flattering to the classified systems. And they go on to test the DT240. They go on to benchmark that, and you can see here, even in the worst case, I think it's 99.6%. So very similar to the locked efficiency of the one-to-one case in the classified, which is basically, as we established from looking at it, is just acting like a normal hub in that case. But there are quite a few omissions from this numerical prediction and the bench test method in this document. And I'll just list a few of those things. Now, in the bench test, there's no simulation of rider weight. So rider weight of the bike plus the rider, that could be, for me, over a kilonewton. So I'm over, probably with the bike and all the equipment, probably over 100 kilos. That's over a kilonewton. That's extra load going down radially on all the bearings in the system. That isn't simulated by the bench testing rig, as we can see here. It's a back-to-back torque rig. The thing's bolted together. It's essentially weightless, and a perfect torque is applied. They do simulate rider weight in the numerical method, so that's in the numerical method, which is good to see. The next thing they don't look at is chain forces. So although the torque rig will apply a torque and a power, the chain forces on a bike are very sinusoidal and very, very peaky. Now, specifically if you're riding a steep climb like I was in my testing and using quite a low cadence, those peak chain forces are going to be quite high, and the torque testing machine, to my knowledge, can't apply a pulsing torque, and that pulsing torque is going to be worse for efficiency. So that is what my testing will show. Now, really, there is some pulsing in the torque test regime, because it looks like these are driven by DC motors, which will be driven by a control algorithm. They will be actually pulsing or cogging in some small, very small pulses, and vibration will be apparent in that, but it won't be anything like a 2 per rev sinusoidal wave like you'll get when you're actually pedaling with high chain force. And I think that's probably worse for the efficiency. I'm not sure. The other thing it can't pick up or simulate in this bench test is transients and vibrational losses. Everything inside this will be vibrating. The balls in the bearings will be vibrating. The gears will be vibrating. The little needle rollers inside the planets will be vibrating. Everything has a clearance. So how do transients affect the efficiency? Now, on the road, you might not think that's a problem, but even on a very, very smooth road, you're still going to get very high frequency vibrations going into the wheel. On gravel, that's going to be even worse. Finally, this can't simulate the effects of the chain line and the chain tension. Now, ironically, that's one thing this is supposed to do pretty well, because it allows you to use a bigger chainring and bigger cogs at the back, because it's got the reduction ratio. So you can drop, if you're using a 50 chainring, not a 34 chainring, you're actually lowering the chain forces by about 45%. And also the articulation of the chain round tight curves is worse. And Classified have actually told me that even with maybe not the best chain line, using the larger chain rings can actually offset the efficiency loss of using the reduction gear. And actually the efficiency can be higher than in a 1-to-1 ratio with smaller chain rings because of the articulation and the chain forces being so much higher. And it's really worth noting that the chain forces don't just act on the hub bearings, they act on the bottom brackets as well. So obviously when you put a torque on the crank at a certain power at a certain speed, the force is transmitted to the cassette by a tension in the chain. That tension in the chain is basically trying to pull the wheel forward in the bike and pull the bottom bracket back. So if you've got 45% lower chain force, you've got 45% lower radial force on all the hub bearings and the bottom bracket bearings as well. And you know, we've got load dependent losses in the hub, but also got load dependent friction losses in the bottom bracket bearings as well. So using the reduction gear in here and the bigger chain rings, classified as said, in some cases can actually improve the efficiency of the whole system when you take into account those extra bearings and radial losses. And anyway, finally, that's why I kept the 2x system on my bike. And it wasn't just to troll YouTube by having 44 possible gear ratios, it was so I could do this test back to back in a 1-to-1 configuration, locked using the 34 chainring and then using the 50 chainring in the reduction ratio with the same number of teeth on the back. So I was using a 34-30 in locked 1-to-1 and then a 50-30 with the reduction ratio. So the overall gear ratio is exactly the same. One's using the reduction gear with all the associated losses, and one is using it in a 1-to-1 like a normal hub. And that is, you know, that takes into account the chain line effects, the bigger chain rings, the lower articulation, the worse chain line. It takes into account the whole system. So it's not just the efficiency of this we're looking at, it's the whole system, including the chain, all those radial forces, even the loads on the bottom bracket will come into play. Everything will slow you down. And if you do an energy calc method like I did of going up a climb at set power, there's no hiding. As long as your standard deviation of all the locked runs or all the reduction ratio runs is lower than the actual time difference you're getting between both, then we're good to go. So wait for that video, it's going to be super good. We're going to put it to bed, hopefully, for better or for worse. I've got no bias, I don't really care which is better, I just want to know what's fastest, because if this is fastest, I'm going to put it on my road bike as well, and God knows, maybe even my TT bike. So cheers, and I'll see you in the next one.